Hello and welcome to episode number 6 of this lecture series. As always, there's a perfume of the day, and today it is an extraordinary perfume called Le Cri, which means the scream, and it's by a company called Parfum d'Empire. It's a small French niche company. And I spray it on while I speak because I don't want to miss the top notes. The very beginning of this fragrance is one of the best first movements, so to speak, of a fragrance that I've ever smelled. It's a combination of rose, jasmine, and herbs, and it really is, and iris. And it really is one of the most extraordinary first 10 minutes of any fragrance you can buy today. The rest is great too, don't get me wrong, but the beginning is simply outrageous. This is a private pleasure. Most people would probably not smell it when you put it on, because unless you rush out. But it's just absolutely beautiful. The perfumer is called Marc-Antoine Corticchiato. I'm not pronouncing it right because he's from Corsica and I'm Italian. And so in Corsica, they don't pronounce it the Italian way. They would say Corticchiato, but that's how it is. Anyway, beautiful fragrance. So today we finally get into the actual business of molecular vibrations. And what I've told you before is that we smell functional groups, we smell the rest of the molecule. The rest of the molecule is pretty much represented in its fingerprint spectrum. And I've told you, for example, in the case of sulfur compounds, that the smell of the molecule is often the sum of, so to speak, the carbon skeleton of the molecule, what the molecule would smell without the functional group, plus the functional group. So that means that if molecular vibrations are going to actually determine smell, that means that changing the functional group should have rather little influence on the fingerprint region. So that means, for example, that if I have a molecule like citronellal, which is a 10-carbon skeleton with an aldehyde group on the end, which is C double bond OH, and I replace the aldehyde group by, let's say, a nitrile group, the overall impression, which is determined by the carbon skeleton, should remain the same, and the character of the functional group should be added on top of that. So now let's see if that is actually correct. So here is the structure and the vibrational spectrum of citronellal. And you can see that it has features that I described before. It has, on the left, it has the fingerprint region, and on the right it has functional groups. So I will show you in a minute the actual animation of each of those vibrations so you will understand better. But for the time being, I want to show you a very simple thing, which is that if you compare the spectrum of citronellal to the spectrum of citronellal nitrile, which is the same skeleton but with a different functional group, a nitrile group, you get a very similar fingerprint region. Now, what do these two smell of? Well, citronellal smells of lemongrass, and citronellal nitrile smells of lemongrass with a metallic note attached. That metallic note, as I've said before, is typical of the nitrile group, and you will find that metallic note in all nitrile containing odorants, whatever the rest of the molecule is. So this is a very important property of vibrational spectra, that in many cases the fingerprint region on the left is completely independent from the functional group on the right of the spectrum. So you may ask, how did I get these spectra that I'm showing you of the different molecules, different functional groups and so on? Well, I get them by using a quantum chemistry software, of which there are many. The one I'm using for this is called Spartan, and it's made by a US company called WaveFun. And it is remarkably easy to use, and you can build molecules quite easily with a menu. You click the atoms together and you get a molecule, after which, once you have the molecule built up, you can calculate all sorts of properties of the molecule, including vibrational spectra. And what is particularly nice is that Spartan makes it easy for you to animate vibrational spectra so that you, once you've calculated the different vibrations, you can click on one vibration and see what the movements of the atoms are. Let me explain an important thing about these vibrations. Any molecule made up of n atoms has 3 times n minus 6 vibrations. So 10 atoms would give you 3 times n, 30, minus 6, 24 different vibrations. So you can see that even a fairly small molecule will have lots of different vibrations, and that each vibration is actually smooth. The exact precision of measuring a single molecular vibration is never achieved. There's always a little bit of play because of the instrumental problems, because of thermal motion and all sorts of other things. So the spectra are not represented by super sharp peaks, at least not in the solution, not when you have a liquid. In a gas they would be. But by rather smooth curves. So now let us look at the spectrum of citronellyl nitrile, which we've been talking about. And I'm just going to move the cursor of the software to different parts of the vibrational spectrum. So first of all, the number one thing you notice is that the lower the frequency, here we're at about 490, we're in the almost in the thermal range. The lower the frequency, the more atoms are involved in a vibration. These modes are very soft. They are basically involve large masses in the bending of bonds rather than the stretching. So this is a very soft mode at 438. So let's have a look. There's an even lower frequency one here. Let me find it. Not so easy to find. There we are. That involves the rotation of carbon groups over a single bond, which is a very soft vibration. The forces keeping them in the right position are weak, and the masses are decently high, so you get a soft, you get a low frequency soft vibration. Now, as we go up, let's see what this guy is, for example. Now, that fellow, let me see. So that is a what's called a CH-WAG vibration, and that is one of the softer modes involving carbons and hydrogens. And you can see that mostly in this particular vibrational mode, most of the motion is concentrated on 3 carbon atoms, but the rest of the molecule jiggles about a little bit as well. Now let's go up. We're now in the fingerprint region. That is a mode of the methyl groups, the CH3 groups. Now we go straight up into the, let's look at this bigger peak here. And that involves a few atoms, some oscillations of the methyl groups at the end, plus some moving around of the hydrogens in the middle of the molecule. And let's go further up and have a look at what happens. Oh, these are interesting vibrations. They're oscillations of the hydrogens as well, and including some stretching. You can see that the bond on the right, the bond between the 2 carbons, is being stretched. Now let's look at this vibration. That's a scissor vibration of the hydrogens. Then there is a scissor vibration of these hydrogens, and then there is a complicated motion here of all sorts of different hydrogens. And then there's a now we're getting into higher frequencies. Actually, this particular vibration is miscalculated by the particular settings of this software. It should be lower. It should be about 1600, not 1800. But it is a carbon-to-carbon double bond, and you see that a double bond is stronger than a single bond, so the spring is stiffer, and you will get a higher frequency of vibration from this. So that's a pretty strong vibration. And then, as we go up, we expect at some point to find the nitrile vibration, and indeed we do. Here it is. And that is the C triple bond and stretch. And again, in this particular rather rapid calculation of vibrational frequencies, the software gets this one wrong. It should not be 2350, it should be 2150, but you can calculate it very exactly to within 3 or 4 or 10 wave numbers using more time-consuming computational methods. I'm just doing this as a simple illustration. Now, look at this peak, the last peak on the right. What is it? Well, it is made up of all the different carbon-hydrogen vibrations, stretch. And you can understand really intuitively why hydrogen is the lightest element. And so, given the particular strength of the spring, it will vibrate at a very high frequency because the mass is small. So let's see. Here's a few more. They're all carbon-hydrogen stretches. But they're not all at the same frequency, even though they are CHs. There is a spread. Now, I cannot guarantee to you that with this method of calculation, those frequencies are exact. But that is the general idea. So you might ask, well, if the vibrational spectra of molecules fit the facts of smell rather well, as we've seen, how come the vibrational theories of Malcolm Dyson, of Bob Wright and Clifton Malone, etc., haven't received more attention? The answer is really quite simple. As I've mentioned before, in the case of Bob Wright, there was no mechanism by which cells could detect molecular vibrations. If you're going to suggest that when you inhale something like this magnificent perfume, that what your nose is doing is actually behaving as a spectroscope, then you have to provide a mechanism. And the reason it's hard to provide a mechanism for the nose behaving as a spectroscope is that all, or actually as we shall see in a minute, almost all spectroscopes are optical instruments. And they involve either visible light scattering off of something, in the case of Raman spectrometry, or infrared light being absorbed by something, in the case of infrared spectrometers. When you look up someone's nose, you see no such thing. You don't see any light sources, you don't see any optics, you just see cells. And it was a perfectly legitimate objection to the vibrational theory that there was no obvious mechanism by which a cell, much less a protein, any living thing, could do vibrational spectroscopy. And that is a tremendous objection. And this is where I come into the story, because I was very interested in molecular vibration theory, but I thought it was crazy. But it did seem to fit the facts rather well. And I had this in the back of my mind for several years. And then one day I was working at University College London, and I was in the library, and I was reading a wonderful periodical journal called the Review of Scientific Instruments, which has page after page of the most ingenious devices designed to measure one thing or another. And I came upon an article that described a, quote, easily realizable, that's arguable. I think you'd have to be still pretty good at it. Electron tunneling spectrometer. So I'd never heard of a machine using electrons that could measure molecular vibrations. So I'm reading the pages of this article, and it actually refers to a rather simple version of something which had been discovered many years earlier by two scientists called Bob Jaklovich and John Lamb. And the principle of the electron tunneling spectrometer is rather simple, and I will explain it later. But what was amazing about it, to me, when I read this article, was that I suddenly realized that the physics that they were describing in this article and that had been discovered by Jaklovich and Lamb were perfectly adaptable to biology, that all the bits and pieces, if you want, of an electron tunneling spectrometer were present in biological systems, that all you had to do was put them together in some clever way, and then you could do spectroscopy with cells, with proteins in the nose. So as you can well imagine, I was pretty excited when I discovered this, particularly since my interest in smell had gone as far as, collecting perfumes, smelling raw materials, going to labs that make perfumes to smell all the different ingredients. So I knew something about smell, and I also knew a little bit about electrons in biology. So I thought, look, this is really, if true, this is really something huge. I mean, after all, there aren't that many senses, and the olfaction is still mysterious. So if this is the solution, it's really worth basically spending the rest of my professional life on. But this was a big decision. And so I felt that I needed to find one fact which really would be, at least for me, definitive evidence that I was on the right track. It wouldn't be a worked out proof of theory, but it would be such strong evidence that it would make me feel confident that I could jump into it and work on this from then on. And I fastened onto a very simple idea, which was the fact that SH, as we've seen, it gives any molecule that it's attached to a quote unquote rotten egg smell, sulfuraceous smell, and that nothing else does. So that, as we've seen, OH never smells of SH, SH never smells of OH, and there's no other functional group in nature that gives a molecule a sulfur smell. And the peculiar thing was that when I started looking into it, the vibration of the SH was also unique. Not just the smell, but the vibration. So this is great because it fits the idea that vibrations control smell. But then it suggested a very simple experiment, if you could do it, which was find another something, functional group, assembly of atoms, I don't know what, but some chemical thing that vibrates at the same frequency as sulfur, which is 2550, 2600 wave numbers, and see if that smells of sulfur. So at the time, I was completely ignorant of where to find the data on molecular vibrations. I mean, now I could find it in like 5 minutes, but at the time I had absolutely no idea where to find it. So it took me literally weeks or months, and this was before the internet, so everything was slower in those days. And eventually I discovered, I was on holiday in Lisbon, and I went to a bookstore, a beautiful old bookstore with wooden shelves and wooden balconies where you could look at the books. And I found a very old chemistry book written by a professor at Howard University in the US, and it was describing molecular vibrations, and it gave the various strength constants of bonds and the masses and everything of various arrangements of atoms, so CH, CO, and I looked down the list, and there's one that says BH, And it looks to me, so B is boron. And boron is just before carbon in the periodic table. And it gave the strength constant of the boron-hydrogen bond is rather lower than that of the carbon-hydrogen bond, and therefore you'd expect the vibration to be lower. So using the formula and my little calculator, I calculated the frequency of vibration of that particular bond, and to my amazement, it came out to about 2550. So I thought, if I can find a molecule that has a BH in it, it should smell of sulfur.